Today our topic is metal properties. We'll be going over the various metals that we'll be using in this course. If you've taken a course maybe in sculpture, you may have primarily worked with steel. Again, I think I mentioned this on the first day of class, but we will be working with non-ferrous metals. Non-ferrous meaning that the metals that we use do not contain iron. We have a sheet, a handout that's called Metal Properties. You'll see it right here. And on that metal properties sheet, you'll see that we have categories where the metal is listed on the left-hand side, and then we have the composition or the alloy, and then we have the annealing temperature and the melting temperature. I'd just like to go through some of those metals that we'll be using and kind of talk about each one. These will all be metals that you could purchase for the use in projects, and again, I will provide you with copper and some yellow brass, but I wanted to kind of talk about some other metals that you might be interested in utilizing. So the first metal on our handout is labeled aluminum, and you'll see that there's a composition of 100% aluminum. There are alloys of aluminum that contain other metals, and an example where aluminum might be used, you've probably all seen something like this called diamond tread plate. This is usually used on truck boxes and things of that nature. We see aluminum used in applications where weight is an issue. So aluminum is a lightweight, strong metal. It is fairly soft, it scratches very easily. But the metal the aluminum is, obviously used in aluminum cans. But also we see this used in aerospace, high-end or higher-end bicycles, aluminum parts for cars and motorcycles, things of that nature. The interesting thing about aluminum is that we can take aluminum and run it through a electrochemical process, and it can be dyed. These are examples of aluminum that have been soaked in a dye after they've been run through the electrochemical process that builds pores on the surface of the metal. And this is actually a technique that I focused on in graduate school and experimented with various resists and patterns that could be applied to the surface of the metal. And again, it's almost an endless palette of color that you're able to achieve with aluminum, and it can be quite fun to play with. One thing to note, aluminum is relatively cheap. You can access it and find it locally in town, as I think I talked about some metal sources here in town in Boone. But you can find aluminum sheet. I do have aluminum sheet. I will give you a little bit of this. We will be doing some etching with aluminum, but it's a great material to work with, very lightweight. Now, one last comment on this is that aluminum cannot be silver soldered or high temp soldered as we will with some of these other metals that we'll speak about today. So it must be cold connected. Now, it can be connected with heat processes, so it can be TIG welded, it can be MIG welded with a spool gun, but those are processes that we typically don't have access to here in this studio. We do next door in sculpture. It's very difficult to do some of those processes unless you have a small laser welder or something like that that can deal with the scale at which we work at. So any connections that you make between your aluminum pieces must be a cold connection, riveted, micro bolted, tabs and slots, things like that. So do keep this in mind, because a lot of students wind up saying, oh, I'll use aluminum because it's a cheaper material to work with, more affordable, and they wind up forgetting that they can't solder it, and they have to rely on cold connections. So just keep that in mind. Our next material that we'll talk about is yellow brass. So this is yellow brass, and yellow brass you'll see used a lot in bathroom fixtures, plumbing. You'll see this used as a connecting device. It's quite strong. And so it's resists corrosion when it's near water, so you won't see any corrosion buildup on this. Strong metal, and we work with this quite a bit. It's a good material for us to be able to get a kind of a yellowish colored metal. There is another brass called red brass. This is red brass. So I'll just kind of compare those. So you'll notice there's more of a reddish tinge to this material. And if you looked at the alloy, the composition, you would notice on your handout that yellow brass has 65% copper and 35% zinc, and red brass has 85% copper and 15% zinc. So you're seeing the copper, the red of the copper, change the color of this. And so again, if you decide you want a slightly darker or more reddish color to your brass, that would be something you could select. And both of these can be silver soldered, high temp soldered, with no problem, with no issues. Another material that we'll occasionally work with is bronze. This is a piece of bronze. We see bronze used a lot by artists in sculptures, so it's cast a lot. It's a great material to cast with, and so it melts down easily. It fills the voids of molds. Can actually be cast fairly thin, and so bronze is a great material for applications where you do want to cast something, but you can work with a sheet material as well. And you'll see bronze used a lot in bushings and bearings, where you've got maybe a steel surface rubbing against that bushing on the inside, and so it's great for moving parts as a bearing surface. You also see it used a lot near water as well, right? Because it can resist corrosion. It will build up over time a slight patina, a greenish patina, more quickly than or a darkish patina more quickly than brass, but great material to work with. It can also be silver soldered, by the way. New gold. New gold is listed here. There is no gold in new gold if you look at it. And on the composition sheet, you're looking at 88% copper and 12% zinc. So you don't see this used as much. When I was a student, we used quite a bit of new gold and would get it, but I don't see it being used a whole lot recently. But it just has a slightly more golden color to it. So if you are interested, I'm sure you can seek this out and get new gold. Can be silver soldered as well. Now, the main material that we'll be working with this semester is copper. This is a sheet of copper. You'll notice that you have the composition is usually 100% copper, right? It's not an alloy usually of anything, otherwise it changes what it is and what it's called. So we'll just be working with 100% copper. And this is a great material to form, to shape in sheet, and we can silver solder this. Later on, if you are interested in more metals courses, we do teach a metal forming class where students learn how to shape a sheet of copper, hammer it over forming stakes through a process called angle raising, and you're able to, from a continuous sheet, create cups, vessels, forms that are quite volumetric. And so this is the main material that you'll start working with immediately for surface embellishment techniques that we'll be doing. Our next material on our sheet is listed in our golds, various carats of gold. I don't think that you'll probably be working with gold in this class unless you have a lot of money and you want to work with it, but typically we don't work with gold in here. And then lead I'll also skip over. Lead is not good to work with these materials, but I wanted to show and list it on that sheet that we have, so you can see there's lead. Nickel. Nickel is a white metal that we will work with. You'll notice it's 65% copper, 18 nickel, and 17% zinc. It's a very hard metal. One of the places you see nickel is even on the the vanes of a jet engine, like the actual rotating part. So you think about that, if a bird can be sucked through an engine like that, this can withstand a lot of punishment. It is a difficult metal to form. And you know, when I took my first metals class, I think my first project, I decided I wanted to work with nickel, and of course it was this like repoussé piece, which means it's a hammered texture where you're actually hammering from the backside, or not a hammer texture, but a hammer forming technique where you're pushing the metal from the backside forward. And man, I had to just wail on the piece to get it to move at all. So it's not even close to copper in terms of being able to form it, but it is beautiful to silver solder with, because your silver solder seams are typically, they blend a little bit. There's just a slight color differentiation between them, but a lot of students like working with a white metal for various reasons, and if that's the case, they might gravitate towards nickel because it's more affordable than silver or sterling silver, but yet you still get that white like surface. It's a strong material though, so it's great for making you know, hollow constructed forms that you don't want to dent, or you're worried about taking a bit of damage. So great material though, polishes up beautifully, holds its surface for a very long time. In terms of tarnish, it takes a long time for it to tarnish. So great material. Niobium I'm going to skip over for a second. Platinum is on our list. Platinum we won't be working with. Again, a very expensive material to work with. You might work with that later on if you got a job as a bench jeweler or something like that, but we won't be working with it. Now silver, you'll notice we have two silvers listed. We have silver and we have sterling silver. You might want to write in your notes that silver is sometimes referred to as fine silver, and fine silver is 100% silver. There's no other metal added to it, and so it is a very soft material. It's wonderful to work with. It doesn't harden that quickly, so it's good for forming and shaping. And if somebody has like reactions to sterling silver because of the copper content, fine silver might be a nice alternative to that, although it is fairly soft, so it deforms easily as a piece of jewelry. So, but we work with it in terms of making wire, like jump rings, fine silver jump rings. It can be fused to itself, which is a neat kind of attribute of it. We don't have to use silver solder in some instances where we're just like, you know, bonding a ring or a jump ring or something like that in wire. Sterling silver is the other material. I don't have a piece of fine silver here, but sterling silver also is a white metal. You'll notice it's kind of a very whitish colored on the surface there, and then when you polish it, just to show you kind of difference, nickel's a little darker. You can see that in the camera or not, but sterling silver we will work with. That'll be one of our first assignments that we'll do with our silver band or ring, and you'll all be using a piece of silver to make that. And it's the addition of copper. You'll notice it's 92.5 silver and then 7.5 copper. The addition of the copper makes it much stronger to be able to withstand deformation, but it still cuts beautifully, forms beautifully. You'll see a lot of metal formed objects as well in silver, but it is expensive, both fine silver and sterling silver. The prices always fluctuate, so you can look at you know, Rio Grande or places of that nature to be able to see what the current prices are, but they do fluctuate up and down. You know, when I was a student, I used a lot of silver. I think in a lot of programs you're seeing less and less students work in silver just because of the cost of it. But at times, you know, when I was a student, I would try to order it or buy it when the prices were low, and then try to keep it on hand. But it is a wonderful material. This will be your first sawing experience, which a lot of people think maybe might be interesting to do that, but I think giving you this nice piece of material to work with, it makes it so you want to invest your time in it. So look forward to that. That'll be happening soon. Now I'm going to jump back to niobium and titanium. I don't have a piece of niobium here necessarily, but I do have a piece of titanium, and both of those metals are considered reactive metals. Now I mentioned earlier that aluminum could be colored. Titanium and niobium can also be colored, and I'll see if I can find a piece of material that I have colored in titanium, but it's done a little bit differently. In this case, we're doing an electrochemical process for aluminum, and then we're sticking the material in dye. In the case of titanium and niobium, to color it, you could use a torch to heat it, and it would actually change colors that way, or you could do an electrochemical process, but the voltage of the current that you're running through is what gives you a spectrum of colors. And let me see if I can find a piece real quick. Yes, here you go. So here's an example, you know, of how you can start to get various colors on titanium. I believe this one has actually just been, these are kind of dull here, these colors, but if you've got the piece prepped and polished, you can get, it's almost like oil or water on oil out in like the parking lot. You'll see this kind of spectrum, right, that you can achieve, and this can be controlled in a much more controlled way than what you see right here. So titanium and niobium are really interesting materials to work with. Titanium is basically the lightness, essentially the lightness of aluminum, but the strength of steel, and so you see this in very high-end bicycle parts, even internal engine parts in like NASCAR engines, stuff like that, F1 race cars. You'll see a lot of titanium, very high strength to weight ratio, and it is a little bit tricky to work with. It's a very hard material. We can saw it though with our jeweler's saw. It can be cut, and to manipulate in terms of forming is difficult. It just doesn't want to move. I mean, we can move it a little bit, but it's pretty tough stuff. And so when it comes to connecting it in our metal studio, we also have to work with cold connections for both titanium and niobium. They cannot be silver soldered, but they can be TIG welded. Again, next door in sculpture, it is possible to do that. You see titanium used a lot in implants, right? Even in the body, it resists chemicals, you know, chemicals from the body deteriorating it. So really, again, an interesting material to work with, and some students are interested in this, and you are able to work with it if you'd like to. It's up to you. We do not provide that for you, though. You'd have to order that on your own. And then I just have a chunk of steel you can see here. It's not on our list, but I like to bring it in. And a lot of times we'll talk about how to source materials. And one of the things that I like to do is you know, kind of scrap, right? Look for scrap and try to scrounge for materials. So one of my students had asked me in the past, you know, how do you tell what a metal is? Well, I will point out that most of your non-ferrous metals that we're working with right here, you know, in this that I've introduced to you, most of these metals will not spark when you touch it to a bell sander or a grinder. So none of these, except for when aluminum has been anodized, it will initially throw a spark as it grinds through that hard layer, because this layer actually of anodizing actually hardens the metal and makes it resistant to coloring. So that one might spark a little bit in the beginning, but once you break through that surface, it will stop sparking. But the rest of these will not throw a spark. But titanium, right, and steel both will throw a spark. And there are various handouts. I've got a few on this, but you can basically base the material qualities, and steel comes in various alloys as well, but you can tell how high of a carbon content or how low of a carbon content steel has by the spark that it throws. And the same thing, well, a similar thing in terms of recognizing titanium is that if you grind titanium, it also will throw a very, very bright spark. And so if you're interested, I can show this in class at some point when we're back in person, and I can show you the various. This is just a brilliant white spark that titanium throws. And you do have to be careful. Some of these, even the shards of some of like titanium specifically, is flammable. So when you're cutting it or you have dust or particles left over from it, it is flammable. It can catch on fire. So you have to be careful with that. But again, steels that are higher carbon content versus lower carbon content are going to have a different colored spark, you know, as far as like how that looks when it's thrown off the machine, so as we grind it. So I just wanted to point those things out. When we come back to the handout, you know, you might ask yourself, well, why does all this matter? The issue that we have with knowing these different characteristics is, first of all, knowing how to work with it, knowing at what point it melts, right? Melting temperature is important to know. And then the annealing temperature. And the annealing temperature is kind of the next thing we want to talk about. And the reason for that is that we're going to be doing some surface embellishment samples, and the surface embellishment samples, we need to prep the metal ahead of time to accept the roller printing or the stamping that we're going to do to it. And so before we impart any sort of like physical stamping or act to or forming of that metal, we need to make sure that the metal has been annealed. And the annealing refers to opening up the pore, or not the pores, but the crystalline structure of the metal so that we can then, you know, work with it. Now, if any of you have ever taken a piece of material and you've taken that and you have bent it back and forth, right? You've worked it and you're like, you know, back and forth, eventually it has most likely broken or snapped at some point. Now, what's happening there is the crystalline structure of the metal is, as you bend it, is getting packed tighter and tighter and tighter with every bending of that material. And eventually the particles, the crystalline structure has nowhere to go. It can't get packed any tighter, and the metal snaps. And so that process of imparting a physical act on the metal until it hardens is called work hardening. That's a term you should know. So it's called work hardening. So by annealing the metal, which typically involves heating the metal to its annealing point, we're able to spread those molecules, a crystalline structure, back out, and then we can bend the sheet and work harden it, and to a certain point to get stiff or rigid, and then we can heat and anneal again, and then we could do more forming to the piece, and it would work harden, or, you know, and as we did that process to it, and then we could anneal again, and you can keep repeating that cycle over and over and over. So if you've ever been to a museum where you see these beautiful silver vessels that are like, you know, those they're like volumetric and, you know, multiple components added to it, those were typically formed out of a single sheet, and then it went through a process of annealing, hammering, annealing, hammering, annealing, hammering, until they got the form up to the shape that they want. And so you can anneal as many times as you want. There is no limit to that. And I always get the question, because we're gonna be annealing in class, and I always get students to say, okay, well, if I anneal and then I put my annealed pieces in my toolbox or my kit, or I take it home with me, but I don't do anything to it, when I come back the next day, is it still annealed? And yes, it is. It's still annealed because you have not imparted a physical act on that piece of metal. So that's going to be our next step, is to teach you how to shear metal, how to heat, and then anneal. So we'll get to that in just a second. All right, one thing to mention about our metal properties handout is you'll notice that in the annealing column, it not only has the annealing temperature, but it also has then whether the object should be quenched or air cooled. And quenching just refers to dunking the metal into a container of water while it's at its annealing temperature, versus air cool, which it basically refers to letting the metal just cool down naturally. So you would take it up to its annealing temperature and then remove the torch, turn it off, and then just let the metal cool just without dunking it. So make sure you know that quenching term. That might be a good quiz question. So quenching just refers to dunking the metal in water once it's up to its annealing temperature. If you flip over, you've got an actual handout that is specifically on annealing, and it goes into a little bit more depth about the annealing procedure, so make sure you've read that. And then it breaks down what we're looking for, because a lot of students say, well, how do I know what the annealing temperature, like how do I know when I arrive at that with a torch? And so what we're looking for is under this procedure column. You'll notice that in the case of copper, we will heat it until dark oxides form when the torch is removed, right? Because you're going to build up oxidation on that surface as it's being annealed. So there's various details about this on that handout, so make sure you've read through that and that you're familiar with those various things. Now, I won't quiz you on specific temperatures. I'm not going to give you like details, so don't worry about memorizing any of that. It's just going to be making sure you kind of know terminology and what to look for in terms of the annealing of the metal. So those, just make sure you know that content. Okay. All right, our next handout talks a little bit about relative size and coarseness. Relative size and coarseness just refers to measuring devices that we use within metals. You'll notice that on one side it's coarse, thick, and large versus fine, thin, and small. So, and then it talks about what you call various like sizes or measuring devices of various things. So last class we talked about the BNS gauge. This is the BNS gauge. So it's a device that we are able to measure. Just grab a piece of metal here. And so as I mentioned, the holes mean nothing. All right. A lot of students think you're supposed to stick wire through those. That's just how this tool is produced. So I can stick my metal through here. You'll notice one side gives you the gauge. So this is 16 gauge. On the BNS gauge. If we flip it over, it will give us the decimal equivalent, which is 0.051. Some companies, when they sell metal, they will measure in gauge or decimal equivalent. So this is the BNS gauge. You'll notice that that's what we call the thickness of metal is gauge, right? High-speed drill bits, we use a numbered system. We'll talk about this when we actually get ready to do rivets. But this is a 1 through 60 gauge, so this is 1 being the largest bit and then 60 being the smallest, and then we can actually test our drill bit to see what size it is by inserting it into this drill bit gauge. And wire, we still will measure the wire just by trying to fit the wire into the notch on the BNS gauge, so it's also measured in gauge. Jeweler's saw blades, we're going to be using Jeweler's saw blades. They look, this is a bundle of Jeweler's saw blades, but the Jeweler's saw blades are measured in a numbered system, so we have 6 being the coarsest on this particular sheet, and then there's 6/0, which is 6/0. So if there's a /0, it's 6/0, 5/0, 4/0, 3/0, 2/0, 1/0. 0. And again, we will be discussing those more in depth as we go over our piercing demo. Again, make sure you know sandpaper grades, right? We're looking, or grit, and that is listed as 50, 80. So 50 being very, very coarse, 1500, and it even goes higher than this. So you can go up to like 3000, 2500. So make sure you're aware of this relative size and coarseness sheet, and how we start to use the terminology for various things. There's a handout on fabrication processes next. I'm going to skip over that for now, and eventually we'll be going into this rolling mill handout, and we'll be referring to that soon.